So the last little section in this topic is a section on solubility of group 2 compounds. Now, if you think about what the word solubility means, again, it's maybe quite an intuitive word, just means how well something will dissolve. Trying to think of a bit more scientific way of expressing that, what we really mean is how much of a particular solid you're able to dissolve in water. So if you had a really soluble solid, you would be able to dissolve lots into a certain amount of water. If you didn't have a very soluble solid, you'd only be able to get a wee bit of it dissolved in water. So we've got quite a precise definition you're meant to learn off, and there's quite a bit of detail in here. What solubility is actually defined as this: it's the maximum mass of a solute, so a solid, that would dissolve in 100 grams of solvent at a stated temperature. So importantly, the standard volume used, or standard mass used, is 100 grams. The solvent generally will be water, but I guess it could be other things as well. And importantly, it has to be at a stated temperature, because as we'll look at, the solubility does change as temperature changes. So maximum mass of a particular solute that will dissolve in 100 grams of a particular solvent at a stated temperature. So there's two parts to this bit on solubility. We have to first of all know a little trend in the solubilities of the group 2 compounds, and then we've got a little section on some calculations we might have to do using some solubility values. So first thing's the trends. It's a little bit of a simpler trend in that you don't actually need to be able to explain it, you just need to recall it. So it's of two particular types of group 2 compound, the group 2 sulfates and the group 2 hydroxides. The solubility of the group 2 sulfates decreases down the group. So what that means is that, for example, magnesium sulfate will be quite soluble in water, but barium sulfate will be very insoluble in water. The opposite trend is true for the group 2 hydroxides. They become more soluble down the group. So magnesium hydroxide will not be very soluble, but barium hydroxide will be quite soluble. It can be a wee bit confusing because you're not actually given any explanation for that. You actually just have to accept it at this point. It's basically to do with some mathematical values for energy changes for solvation, but you just have to learn it for now. Little revision tip that might help you learn it. Can't remember where I saw this, but I think it's quite good. If you look at sulfate, we know the formula for sulfate is SO4 2-. If you imagine the bottom of that 4 could be a wee downward arrow, because the solubility decreases down group 2 for the sulfates. Hydroxides you could express like this, the little OH- for hydroxide, with a wee arrow going up from the H because the solubility increases down the group. There is another wee revision tip you can use to help you remember that trend. If you remember back to 1.10 qualitative tests, the substance you use to test for sulfate ions is barium chloride, specifically the barium ion there. That test works because you get a precipitate formed when you mix barium with a sulfate ion, so barium sulfate is insoluble. So remembering that barium sulfate is insoluble and barium is quite close to quite close to the bottom of group 2, would help you remember that the solubility of the sulfates decreases to become very insoluble at the bottom of the group there. So just to give you that wee equation to remember, so barium ions, Ba2+, when you bring them towards sulfate, they're very insoluble. You'll form a precipitate when you mix those two things together in solution. So that's a couple of trends. In terms of a little bit of mathematics with regards to solubility, it's to do with measuring or getting the effect of temperature changes on solubility. Now that should be something that's a wee bit intuitive to you. Probably in this lockdown you've probably made quite a few cups of tea, and you should know intuitively that if you're trying to dissolve a wee bit of sugar in your tea, it's going to be much easier when it's hot tea versus cold tea. Solids tend to become more soluble when the water is at a higher temperature. So you can keep track of that by using what we would call a solubility curve. A solubility curve is just a graph, and it measures the solubility of a substance as temperature changes. So the graph has got a standard format. You have solubility in grams per 100 grams of water on the y-axis. You have temperature in degrees C on the x-axis. So looking at this example one here, solubility is measured on the y, temperature on the x. And as we see, as temperature increases of a particular amount of water, the solubility of a solvent will increase. It goes up with a curve. And there are a number of ways we could use this graph. Just maybe one simple way you could interpret this. You can use it to find solubility values at any particular temperature. So if I had a bit more detailed graph, I can maybe look for 50 degrees C I might want to know how soluble a particular solid is at 50 degrees C. I could read up from 50, find that value on the graph, and read it across, and I'm just going to make up a value. Let's say that is 20 grams solubility per 100 grams of water. What that tells me is if I have 100 grams of water, if it's at 50 degrees C, I will be able to dissolve 20 grams of this particular solid in that water. Obviously, if I went to a higher temperature, I'd be able to dissolve more in 100 grams of water. If I went to a lower temperature, I'd only be able to dissolve a little bit of solid within the water. Other ways you can interpret it here, each point on or above the curve represents a saturated solution at the temperature. So we've got a new term there, saturated solution. If a solution is saturated with a solid, it means it can't take any more of that solid and dissolve it. So if you added any more to it, it would just settle onto the bottom of the beaker. So saturated just means that it contains the maximum amount of dissolved solid. So what we mean by above and below, so the next point is each point below the curve represents an unsaturated solution. So talking a wee bit about points above or below the curve. If I stick to that idea, that point I've marked on for 50 degrees C, what that means is if I go above this point, so up to here, that would represent me trying to dissolve, for example, let's make up a value, 50 grams on this solubility curve, or solubility axis. If I tried to dissolve 50 grams of solid in 100 grams of water, at 50 degrees C, I wouldn't be able to. I'm above the curve. My maximum amount that my water can take at that temperature is 20 grams per 100 grams. So if I go above that point, I'm now beyond saturation, so I've got solid sitting at the bottom of my beaker. If I go below the curve, it's unsaturated. Unsaturated obviously means it can take more solid. So if I was to go down, maybe on this point, I'm going to imagine it's 10 grams per 100 gram of water. So if I tried to dissolve 10 grams of solid in 100 grams of water for this particular curve, I would be able to do it because it's below that saturation point, and I would be able to add more and still get to dissolve up to 20 grams there. So that's how I can maybe interpret increases or decreases in the amount of solid I'm dissolving at a particular temperature. A wee question here, why does the temperature axis only run from 0 to 100 degrees C? Hopefully not too tricky to work that out. 0 to 100 degrees C are the melting points and boiling points of water. Because if you're trying to dissolve a solid in something, it helps if that's a liquid. You must have a liquid to be able to dissolve a solid. So if you tried to dissolve a solid in water that was at -10, you basically would be rubbing salt on an ice cube, which wouldn't go that well. If you're trying to dissolve a solid in water above 100 degrees C, you'd be throwing some salt at some steam, which again would not be going very well for you. So it has to be between 0 and 100, it has to be a liquid. So last little bit in that is some calculation work you can be asked to do. This does look a wee bit scary on face value, but it's pretty much just taking two numbers away from each other. It's not the worst thing you've done in terms of calculations this year. So what these calculations generally revolve around is the idea of you taking a solution of a salt dissolved in water and then cooling it down and seeing what might happen. So if I took a beaker that had like a saturated solution of a particular salt dissolved in water and cooled it down a bit, I would probably expect some of the solid to not be in solution anymore because the solubility is decreased. What this calculation is about is maybe working out how much salt would fall out of the solution or be deposited as the solubility decreases. So generally in the exam they would give you a graph. This is like an exercise based graph, so it's giving you lots. Probably the one that would come on the exam would just have one line on it, but we can do a few things with these lines here. And it's probably easiest if we just dive straight into an example. So here's what the question would probably be about. Using the graph, determine the mass of solid potassium chlorate, KClO3, that one there, that will be deposited when 100 grams of a saturated solution of potassium chlorate is cooled from 90 degrees C to 70 degrees C. That can maybe seem a wee bit complicated in the question form. If you actually did this in real life, I think it'd be a bit more intuitive. So I'm going to draw a wee diagram here. What that question is basically saying is, I've got a beaker of potassium chlorate. It's at 90 degrees and it's saturated, so it's containing the maximum amount of solid it possibly can. I'm going to cool it down to 70 degrees C. It now can no longer hold as much solid as it could at 90, so it can't hold the full amount it's got at 90, so some of it's going to settle at the bottom of the beaker. So I'm trying to work out how much is going to settle out at the bottom of the beaker if I cool it down. To do that, I need to work out some solubility values, and that's where I need to use my graph. So if I look for the KCl3 curve here, I'm going to look for 90 degrees C. Again, I kind of have to estimate a wee bit here, it's not a particularly good graph, but that point is there. I'm going to say to my eye that's going to be 47 grams per 100 grams of water. In this case, I do have 100 grams of that solution. So I can just assume that in this particular beaker, if it's saturated at 90 degrees C, it's containing 47 grams of potassium chlorate per 100 grams of H2O. If I look at what's happened as I cool it down to 70 degrees C, I need to look at my curve here at 70. It's along a line, so it's 30 grams per 100 grams of water now. So it's now only able to hold, in solution, 30 grams per 100 grams of water. So if we've decreased the solubilities, what that basically means is that some of it that was in solution is no longer in solution, and it will be found at the bottom of the beaker. Hopefully it's not too tricky to work out how we work out what's at the bottom of the beaker. We're basically going to subtract the solubility values from each other. I've decreased solubility by a certain amount. That decrease will cause some solid to go at the bottom of the beaker. So to work that out, it's going to be 47 grams per 100 grams of water. Take away 30 grams, which means that there must be 17 grams dissolved at the bottom, deposited at the bottom of that beaker once I've cooled it down. A bit more formally, if you want like a table method, essentially what we do is we look up our solubility values. At 90 degrees we've got 47 grams per 100 grams of water. At 70 degrees C it's down to 30. So the difference in solubilities is 47 minus 30, which is 17 grams. So therefore 17 grams of potassium chlorate is deposited at the bottom of the beaker. So it's fairly straightforward in that you're just taking two numbers away from each other. They can make it ever so slightly more difficult. What made this one easy is that in this question we had 100 grams of the solution. What they can do to make it more tricky is they can give you it where it's not 100 grams. You have to use a wee bit of ratio work to get it to adjust the values. So we see a similar question here. Using the graph, determine the mass of solid potassium chlorate which will be deposited when 25 grams of a saturated solution of potassium chlorate is cooled from 90 to 70. So this is quite a nice question to look at because the solid is the same and the temperature change is the same. All we're changing is the amount of water we've got dissolved in it. So your starting point again is pretty much the same as what you looked at in the previous question. You're going to look up your solubility values for those particular two temperatures. So at 90 degrees C, the solubility of potassium chlorate is 47 grams per 100 grams of water, as we looked at before. And when you cool down to 70 degrees C, that solubility decreases down to 30 grams per 100 grams of water. So here's the twist in this question. We've not got 100 grams of water, we've only got 25 grams of it. So we have to adjust the amount of solid that will dissolve because we got less water now. It's still saturated, so that ratio will still be the same. You get 47 per 100 grams of water. We just have to make it correct for what if we only had 25 grams of water. So we have to adjust 100 grams down to 25 grams. That's simple enough, we just divide by 4 in both cases. So if I only had 25 grams of water at 90 degrees C, it would be 47 divided by 4, which is 11.75 grams in 25 grams of water. And again, if I had it down 70 degrees C, divided by 4 again, if I only had 25 grams of water, that would mean I'd be able to dissolve 7.5 grams in 25 grams of water. At this point, the question becomes the same as one we looked at before. I've got two solubility values. If I do a wee diagram just to make it super clear. So I've got smaller beakers of water here. They're both 25 grams, sorry. In this one, it's saturated, therefore it's 11.75 grams of it. At this one, it's still saturated, but obviously that means it can't hold as much. So it's now down to 7.5 grams of water, going from 90 degrees C to 70 degrees C. So some must be sat at the bottom. It's deposited. To work out what has been deposited at the bottom, I need to do a brief subtraction. 11.75 minus 7.5 grams means that 4.25 grams must be deposited at the bottom. Final example, and this may be one of the last variations I can maybe do to make it a bit trickier. They can give you a question where the initial solution of the hot liquid the hot solution isn't actually saturated. So using the graph to determine the mass of solid that will crystallise when a solution that is not saturated, containing 11 grams of potassium chlorate dissolved in 50 grams of water, is cooled from 60 degrees C to 30 degrees C. And this can be a wee bit more tricky because you're going to be tempted to use values in this question that you don't actually need. So I'll try to explain what I mean by that. So if I just approach this question in the same way that I approached this one before, so against potassium chlorate, it's two different temperatures actually. So if I looked at 60 degrees C, the solubility of potassium chlorate, we'll need to look at our graph. So up to 60, it's here, we're going to call that maybe 23 grams per 100 gram of water. I can adjust it down to 50 grams of water just by dividing by 2, because that's the amount of water I've got. So that gives me 11.5 grams per 50 grams of water. If I can link it down to 30 degrees C, the solubility is, let's have a look, 30 is pretty much on 10 grams per 100 gram of water. So again, to adjust that down to 50, which is what I've actually got, divided by 2, it's going to be 5 grams can dissolve in 50 grams of H2O. So the temptation here is just to treat this exactly the same, so subtract those two values and work out what's going to be deposited. The twist in this question is that the initial solution isn't actually saturated. It only contains 11 grams of potassium chlorate and 50 grams, and as you can confirm there, that's not the maximum it can take at that temperature. It can take 11.5. You only dissolved 11. What that means is being careful. I'm going to ignore the solubility value for this calculation because I don't actually have a saturated solution. I don't actually have 11.5 grams of that solid in that amount of water. I've only got 11 grams. So looking at a beaker view kind of here. So going from 60 degrees C down to 30 degrees C. The twist in this question, as I've kind of emphasised, it's not 11.5 grams in 50 grams of water. I've only got 11 grams in here. However, once I do go down to 30 degrees, 11 grams is more than what that water can dissolve at that temperature, so now it will be saturated. So down to 30 degrees C, it can only hold 5 grams per 50 grams of water, which means we will again get some solid deposit at the bottom. So even though it wasn't saturated at 60 degrees C, once you cool it down, it will now become saturated. It can't hold that full 11 grams, only 5. So the question now is, how much is at the bottom? It's going to be the difference between the amount I had at the start versus how much is still dissolved in the solution. So it's going to be 11 grams minus 5 grams, which equals 6 grams of solid deposited at the bottom. So we have now reached the bottom of page 97, which means we've now reached the end of AS2. So that's the final bit of the story of AS chemistry. It's been a bit of a roller coaster to get here, but well done in some trying circumstances getting to the end of your AS chemistry course.